We want to finish up our discussion about ionic bonding by talking about the energy that's involved in these processes. Um, we learned Hess's law in a previous chapter, and once we understand that, we can talk a little bit about how these things happen, because we can look at a process that happens in any number of steps and we can break it down into reactions whose energies we know and use those to calculate um, the energy for the missing step. For example, if we want to talk about the reaction of sodium solid with chlorine gas to make sodium chloride, and we want to find out what that energy value is, we can start out with sodium solid and look up how much it would take energy-wise to vaporize a mole of that. Well, that would be 107 kilojoules. And we can do the same thing with the chlorine. That's already a gas, but we can look at how much it would cost energy-wise to break that bond for a half a mole of chlorine. As it turns out, that would be 122 kilojoules to break a half a mole of chlorine gas and make chlorine atoms, a whole mole of them. We'll do that because we know the energies, the ionization energy for sodium and the electron affinity for chlorine. We know those energies in the textbook. We can look those up in tables and find them, but they are for gas phase exchanges, not for solid. So we take our sodium solid, we vaporize it in theory, we take our chlorine gas, we break it in theory, and these are numbers we can look up. Then we take an electron away from the sodium. That costs almost 496 kilojoules for each mole. But those are all endothermic processes. Putting the electron we took away from sodium onto the chlorine is an exothermic process. And so we get some energy back. Our total energy consumed drops, and that's why we show it this way on this table. We call this a Born-Haber cycle. And then we look at the energy of attraction between sodium ions and chloride ions. As it turns out, for every mole of these we put together, we get back 787 kilojoules per mole, and we call that the lattice energy. So in going from sodium solid and chlorine gas, we use up this amount of energy, the sum of these three numbers, but we get back this amount, the sum of these two negative numbers. The difference between those is the energy for the entire reaction based on Hess's law, negative 411 kilojoules per mole. So as long as we can look up any one of these numbers, any 5 of these numbers, we can calculate the sixth based on Hess's law. And so we refer to this as the Born-Haber cycle. And here's the same cycle and we need a few more numbers this time, for magnesium chloride. If we take magnesium solid and react it with chlorine gas, we're going to get magnesium chloride. Notice that the energy for breaking chlorine is twice as high this time, because we're breaking a whole mole of chlorine gas to get 2 moles of chlorine atoms. For magnesium, we're vaporizing the magnesium. That takes a certain amount of energy to get to gas phase. And then that magnesium gas has to have an electron removed and a second electron removed. And so we've got 2 ionization energy steps. The energy involved in electron affinity for chlorine is twice as high as on the previous slide, because we're doing 2 moles of electrons added instead of just 1. It would be more accurate to drop the per mole on both of these tables, since this is actually for 2 moles, not for 1 mole. And then the lattice energy is here. Now here's the thing about these Born-Haber cycles. The lattice energy is the thing that is much more difficult to experimentally determine. We can experimentally determine sublimation energies and bond energies, or it's fairly easy to calculate a bond energy using quantum mechanics programs. Ionization energies are very easy to calculate and or determine experimentally. Same thing with electron affinities. And the overall chemical reaction energy is easy to determine in a calorimeter. This is the one that we have to figure out by Hess's law, because it's very difficult to do an experiment where we take ions in the gas phase that we have a measured amount of energy for and then convert them to solid. It may actually be impossible to do just that reaction by itself. And so we find out these lattice energies, the energy involved in making the crystal from the gas phase ions, by Hess's law using the Born-Haber cycle. Lattice energies can also be calculated theoretically as a force, where we have a force constant, and that force constant is multiplied by the two charges involved and then divided by the distance between the centers of those charges. So we would expect the lattice energy, and we can look at some examples in the book on this, to be larger, a larger negative number, larger and exothermic, for attraction between ions of larger charges. So for example, when we make aluminum oxide, we have +3 times -2, we have a -6 here, and we get a very large energy. But when we're looking at aluminum chloride, we get a much smaller energy. Aluminum chloride, we get a much smaller energy because we're looking at 3 times -1 instead of 3 times -2 for this term. The distance is also a little bit different, and so we don't get exactly 1/6, we get closer to 1/3 because of the difference in ionic size between chloride and oxide. But still, we can make a pretty good judgment as to which is going to be the strongest lattice energy based on the size of the ion and based on the charges of the ions involved in that compound. And we'll work on some examples of that in class, and there are some examples of that in the suggested homework problems for this chapter that I'd like you to take a look at and work on this week. And we'll try to work on some of these in class as well before we move on to chapter 7 next week.